Okay, good afternoon everyone. Welcome back to SOM lecture series, that is strength of material lecture series. So today we will see bending stresses. Okay, in that first we will see pure bending. Okay, so first we will see what is meant by pure bending. Okay, for that I will draw figure, then we will continue. Suppose if this is simply supported beam AB, and on that beam I am going to apply 2-point loads. Suppose this is point load P and this is point load P. Okay, this distance is A distance, this is also A, and this is L distance. Okay. Due to this application of loading, first we have to draw bending moment diagram and shear force diagram. So first I will draw here shear force diagram. Okay, shear force diagram. Due to this load 1, shear force diagram likewise, and here 0. Okay, after that we will draw shear force diagram for this B support. Okay, for this B support. This is shear force diagram. This is in positive, this is in negative. Here P, here also P. Okay, this is our shear force diagram. Then next I will draw bending moment diagram here. Okay, bending moment diagram. Okay. So bending moment diagram likewise. This is our bending moment diagram and whole diagram is in positive. Now from this figure we have to understand what is meant by pure bend. Okay. See here in shear force diagram, in this portion shear force is 0. In this portion shear force is 0, and in bending moment diagram in this portion bending moment is constant. So pure bending means if shear force is 0 and at that same point bending moment is constant, so this is called as pure bending. Got it? Pure bending means shear force is 0 at same point bending moment is constant, so this is called as pure bending. This is called as pure bending. Now this 2-point loading, due to this 2-point loading, pure bending is occurred. Please remember this thing. Again and again you require this basic concept. Okay, due to 2-point loading, pure bending is occurred, and due to 1-point loading, maximum bending or maximum deflection is occurred. Got it? So pure bending means shear force is 0. At that point, bending moment is constant. So this bending is called as pure bending. So this portion is called as pure bending. This portion is called as pure bending. Already you studied it in Introduction to Solid Mechanics. Just we revise here. Okay. So pure bending nothing but shear force is 0 and bending moment is constant. So this is called as bending. Here only bending moment is present and shear force is 0. So this is pure bending. Okay, got it? After that, then next, second point, neutral layer. Okay, neutral layer or neutral axis. For that also I will draw figure here and then I will explain concept. Suppose this is our simply supported beam. Okay, simply supported beam. In that, suppose this is our axis. This is our neutral axis. This is our neutral axis. Okay, this is our bending. Okay, in this figure here, drawn bending is occurred. Now, neutral layer means the layer which does not undergo any change in length. Okay, so neutral layer means in that layer the length does not change. Okay, for that I will draw figure here also for this bending. This beam bends likewise. Okay, this beam bends likewise. Now, see here. So neutral layer means in that layer there is no any change between length before bending and after bending. This length remains same. This length remains same before bending and after bending. Just you have to remember that neutral axis means there is no any change length. Okay, before bending and after bending. म्हणजे बेंड आपला जो काही बीम आहे तो बेंड होण्यापूर्वी आणि बेंड झाल्यानंतरही हा जो काही लेअर असेल त्याची लेंथ चेंज होणार नाही. त्या लेअरला आपण काय म्हणणार आहे? न्यूट्रल लेअर. And suppose I will join these two parts. So this is called as R, that is radius of curvature. We will see this part in next slide. So radius of curvature. After that, next concept, neutral axis. Okay, neutral axis. Line of intersection of neutral layer with plane of cross section. So न्यूट्रल लेअर जो काही आपला न्यूट्रल लेअर असेल त्याच्याशी लाईनचं इंटरसेक्शन म्हणजे हा कुठला झाला तुमचा न्यूट्रल ऍक्सिस. ऍट न्यूट्रल ऍक्सिस देर इज नो एनी चेंज इन लेंथ बिफोर बेंडिंग अँड आफ्टर बेंडिंग. सो please remember that it passes through CG of cross section. So this neutral layer passes through centroid of this cross section. And also here the axis where the strain changes its sign. See here. This is our beam, okay, cross section of beam, and here strain diagram is given. Okay, strain diagram. Okay, strain diagram. Now see here in this figure, compression is at top and tension is takes place at bottom. Okay, after application of loading, compression is present at top and tension is present at bottom. Now see here, strain or stress in that particular part here compressive, and below neutral axis it is tensile. So compressive strain is positive and tensile strain is negative. So the axis where the strain changes is sign. So above neutral axis sign is compressive or negative, and below neutral axis sign is positive. Just you have to remember that at neutral axis, sign of strain changes. Okay. Then next concept is equation of pure bending. Equation of pure bending. Already we have studied it. Flexural equation or bending equation. What is our equation? Equation is m upon I, which is equal to sigma or f upon y, which is equal to E upon R, which is equal to E upon R. This equation already we have studied it. How to derive this derivation also we have studied it in Introduction to Solid Mechanics. Now you have to just remember this formula, m upon I, which is equal to sigma or f upon y, which is equal to E upon R. Now we will see meaning of each term. Okay, first we will see meaning of this movement, m. So m nothing but m, which is equal to bending moment. Okay, at x-axis or at y-axis. This is first meaning. Second meaning is maximum bending moment. Second meaning is maximum bending moment. And third meaning is moment of resistance. Moment of resistance. Okay, moment of resistance. Now I will explain bending moment. So suppose this is our simply supported beam and this is our point load. Due to this point load, some movement is occurred here, and this is called as bending moment. Now we will see maximum bending moment. Now see here, this is our neutral axis. Above neutral axis and below neutral axis, both dimensions are varied. Okay, according to our diagram. When we are going to calculate strain at extreme fiber, or when we are going to calculate strain at maximum distance. Suppose at top distance is 20 mm and at bottom distance is 30 mm. Okay, y distance is 30 mm. So we will consider this maximum distance and find out maximum bending moment. So this is called as maximum bending. And last, movement of resistance. So when we say moment of resistance. So M which is equal to moment of resistance. If our input in terms of strength, then this is called as moment of resistance. Then this is called as moment of resistance. So our formula is sigma which is equal to M upon I into Y. Sigma which is equal to, or F which is equal to M upon I into Y. Now I have considered here these two terms. So sigma or F which is equal to M upon I into Y. Okay. When this Y distance is maximum of these tools, then this is called as maximum bending. बघा मॅक्झिमम बेंडिंग मोमेंट कधी म्हणणार आहेत आपण, तर हे y चं डिस्टन्स मॅक्झिमम ऑफ these two distances at that time we will call this moment is maximum bending. And when we say when we say moment of resistance, if our input is strength of material, then this is called as moment of resistance. Okay, this is the meaning of M. After that, second part is, okay, our basic equation is M upon I which is equal to sigma or F upon Y which is equal to E upon R. Then this I which is equal to, already you know that meaning of this I is moment of inertia. Then this sigma is nothing but stress. This Y, depth of our neutral axis. This E means Young's modulus and this R means radius of curvature. This is our equation of pure bending. Okay, equation of pure bending. Now we will consider second half portion. Okay, we will consider second half portion, that is our basic equation M upon Y which is equal to F upon Y which is equal to E upon R. Now we will focus on this second half portion. Okay. No, we will consider first and third. M upon I which is equal to F upon Y which is equal to E upon R. Now we will consider these two terms, that is M upon I which is equal to E upon R. Now we will derive equation M which is equal to EI upon R. This EI nothing but flexural rigidity, and this R nothing but radius of curvature. So radius of curvature means this is our bending nature of beam when I will extend these lines. So this is called as the radius of curvature. Okay. Now you tell me, suppose if beam should not be bent, then what should be the radius of curvature? जर आपला हा बीम बेंडच नाही झाला, तो आहे हा ओरिजिनल पोझिशनला असेल, तर रेडियस ऑफ कर्वेचर किती असेल? Anyone please? Already we have discussed this point in introduction to solid mechanics subject. If beam should not be bent, at that time radius of curvature which is equal to how much? Anyone please? बघा काही लक्षात येते का, काय आपण शिकलो होतो? ओके, इफ बीम
असणार ना,
काय असणार?
लेंथ एवढीच असणार ना, रेडियस ऑफ कर्वेचर बेंडच झालं नसेल तर.
No, if beam is not bent, at that time radius of curvature is infinity, or we have to consider bending moment M which is equal to 0 because of beam has not bent. So bending moment is 0. Okay, please remember that. So this is our equation of pure bending. So basic equation is m upon I, which is equal to F or sigma. You remember both notations, divided by Y, which is equal to E upon R. Okay. Then next we will see next concept, assumptions. Okay, we will see next concept, assumptions. So first assumption, the transverse sections which are plane and normal before bending remain plane and normal to the longitudinal fiber after bending. In simple word, I will tell you assumption. Okay. Plane section before bending remains plane after bending. See here, this strain distribution is linear. Okay, this strain distribution is linear. According to Bernoulli's assumption or according to Bernoulli's theorem, okay, this strain distribution is linear and first assumption is plane section. Okay, this plane section before bending and after bending remains plane. बघा, जो काही आपला हा काही स्ट्रेनचा पार्ट आहे, ही जी काही लाईन आहे ही लिनियर आहे, तर ती लाईन बिफोर बेंडिंग आणि आफ्टर बेंडिंग काय असणार आहे, सेम असणार आहे, त्याच्यात कुठलेही चेंजेस होणार नाही. दिस इज अवर फर्स्ट assumption. Then second assumption, material is homogeneous, isotropic and obeys Hooke's law and limit of eccentricity are not exceeded. So first is homogeneous. What is mean by material is homogeneous? When we say material is homogeneous, in last lecture we discussed, when we say material is homogeneous and isotropic, elastic properties are same with respect to direction or at any point.
All directions same, homogeneous.
All directions. And isotropic means
At
Any
one point.
Isotropy means
yes please.
Elastic properties point
homogeneous at any point ला येते ना homogeneous मध्ये, आणि isotropy म्हणजे any direction.
Okay, this is correct. Suppose this is our cube. Now we are going to check elastic properties. Okay, suppose I have checked elastic property at this point, then this point, this point, this point. If elastic properties are same at any point, then this material is called as homogeneous. And if elastic properties are same at any direction or with respect to all direction, then this is called as isotropic. So homogeneous means at any point and isotropic means at any direction. Elastic properties are same. So this is first. Then second, it obeys Hooke's law. Hooke's law means this assumption is valid up to limit of proportionality. Okay, this assumption is valid up to limit of proportionality. And also next assumption is limits of eccentricity are not exceeded. So those limits, these limits are not exceeded. So please remember, homogeneous means properties are same at any point, and isotropic means properties are same at any direction. Okay. Then third assumption. Then next, third assumption. Every layer is free to expand or contract. Okay, every layer is free to expand or contract. Now I will draw some figure here for this assumption. Okay, suppose this is our simply supported beam. Okay, this is our simply supported beam, and on that beam one point load is act. Due to this point load, beam bends likewise. Okay, beam bends likewise. Now from this figure, you tell me compression is act where and tension is act where. On which layer compression act and on which layer tension act?
अप्पर पोर्शनला कॉम्प्रेशन.
ओके गुड. टॉप जो काही आपला अप्पर पोर्शन आहे इथे कॉम्प्रेशन असेल अँड बॉटम पोर्शन टेन्शन. नाउ वी विल फाइंड आउट स्ट्रेसेस at every layer. Stresses at each and every layer. See here, stresses are going to change at each and every layer. Okay, then if we observe this stresses line at bottom, so these lines are expands, and when we observe these lines at top, these lines contract. So this is our third assumption. Every layer is free to expand or contract. म्हणजे प्रत्येक layer हा expand होऊ शकतो किंवा contract होऊ शकतो. This is for simply supported. Now I will draw figure here for cantilever. Okay, for cantilever. Okay, please remember that in cantilever beam, bottom portion compression is at and top portion tension is at. Here also stresses changes with respect to each and every line. So at bottom compression is at and at top tension is at. So at top length increases and at bottom length contracts. So our third assumption is every layer is free to expand or contract. Okay. Then next we will see fourth assumption. Modulus of elasticity has same value for tension and compression. So if we are going to study modulus of elasticity, so modulus of elasticity is same at in tension and in compression. Modulus of elasticity changes with respect to material. Modulus of elasticity does not changes with respect to tension or compression. So this changes with respect to material. So our fourth assumption is modulus of elasticity has same value for tension and compression. Then fifth assumption. Okay, then next our fifth assumption. The beam is subjected to pure bending and therefore bends in an arc of circle. See here, our bending is pure bending. That is, bending moment is present and shear force is zero. So this is arc type bending. And last assumption is a radius of curvature is larger compared to the dimension of the cross section. For that I will draw figure here. This is our bending of beam. Suppose we will join this. So this is our radius of curvature. Okay, this is our radius of curvature. See here, this is our deflection of beam or bending of beam. Okay, this is our bending of beam. This dimension is very less as compared to this radius of curvature. Okay, as compared to this radius of curvature. So our last assumption is a radius of curvature is larger. Observe here, this distance is larger as compared to cross-sectional dimensions. So please remember these all 6 assumptions. First is plane section before bending remains plane after bending. म्हणजे बेंडिंग होण्यापूर्वी सेक्शन हा प्लेनच असतो आणि तो बेंड झाल्यानंतर सुद्धा तो प्लेनच. Then second, material is homogeneous, isotropic and it obeys Hooke's law. Also, limit of eccentricity are not exceeded. Third is every layer is free to expand or contract. That means you have to check stress distribution at each layer. So you observe this third of the assumption. Then fourth assumption, modulus of elasticity has same value for tension and compression. Modulus of elasticity varies with respect to material. If material changes at that time, modulus of elasticity also changes. Modulus of elasticity for steel, which is equal to generally 200 GP. So, and modulus of elasticity wood, modulus of elasticity aluminum, etc. So modulus of elasticity changes with respect to material, does not with respect to compression or tension. Then fifth assumption is the beam is subjected to pure bending. Okay, beam is subjected to pure bending, and pure bending nothing but bending moment is constant and shear force is zero. And last is radius of curvature is larger. This radius of curvature is larger as compared to this cross-sectional dimensions. Okay, These are the assumptions. Then next point is other important points related to these assumptions. Okay. So the strain of a fiber is proportional to its distance from neutral axis. So epsilon, which is equal to y upon r. Please remember this. And second one is the sum of all the compressive forces above neutral layer. Above neutral layer must be equal to the sum of tensile forces below neutral layer. Okay. For that, I will draw figure and explain. Okay. Suppose this is our cross section of beam. This is our cross section of beam. This is cross section of beam. This is neutral axis. Now I will draw strain diagram for this particular beam. Okay. So here compressive stresses are present and here tensile stresses are present. So FC and FT. Now we have to find out suppose stress at that particular point. Here stress. At that particular point here also. So now we will take addition. How to take addition? Integration of all stresses generated at various points in compression. So integration of FC, which is equal to integration of FT. म्हणजे इथे काय असणार आहे तुमचे जेवढे स्ट्रेसेस टोटल स्ट्रेसेस कॉम्प्रेसिव्ह मध्ये असतील तेवढेच स्ट्रेसेस तुमचे काय असणार आहेत टेन्साईल मध्ये जनरेट होणार आहेत. ओके. These are the two important points. After that, next point is section modulus. Okay, already we have studied it. So section modulus, nothing but moment of inertia divided by distance of extreme fiber. So M, which is equal to, or Z, which is equal to, or one basic equation with you, M, which is equal to sigma into I upon Y. This equation comes from flexural equation. M by I, which is equal to sigma by Y, which is equal to E upon R. Here, consider these two parts. So M, which is equal to sigma into I upon Y. This I divided by Y, nothing but Z, and this is called as section modulus. This is called as section modulus. So I by Y, that is moment of inertia divided by distance of extreme fiber, Y. This is called as Y. Next, we have to learn moment of resistance. So MR, which is equal to sigma into Z. When we say moment of resistance, if our input is stress or strength, when we say moment of resistance, if input is stress or strength, yes, please, anyone? Now, just before 5-10 minutes, I told you when we say moment of resistance, if our input is strength, then we say moment of resistance. If our input is strength, then we say bending moment or maximum bending moment. Okay. So strength means strength of material, that is material property. If our input is material property, then this is moment of resistance comes. If our input is stress, then this bending moment will comes. Okay. Please remember that if our section modulus is increases, at that time moment of resistance also increases. section modulus is increases, at that time moment of resistance is increases. Do you agree with me? बघा जर सेक्शन मॉड्युलस इन्क्रीज होत असेल तर मोमेंट ऑफ रेजिस्टन्स इन्क्रीज होतो. ह्याच्याशी ऍग्री आहात का? बघा जर आपण इफ वी कन्सिडर टू मटेरियल्स, फॉर फर्स्ट मटेरियल सेक्शन मॉड्युलस इज 100 and for second material section modulus is 200. Suppose this is Z1 and this is Z. Now we have to find out moment of resistance 1, which is equal to sigma into Z1, which is equal to sigma into 100, and moment of resistance for second material, which is equal to sigma into Z2, which is equal to sigma into 200. See here, MR2 2 times of this MR1. So if section modulus is increases, automatically moment of resistance also increases. Okay, moment of resistance also increases. Now you tell me bending moment and moment of resistance. So if we are going to design any beam, at that time moment of resistance should be greater than or less than bending moment. कोणता जंक्शन करेक्ट असेल? शुड बी ग्रेटर दॅन और शुड बी लेस दॅन और इक्वल टू? बेंडिंग मोमेंट और मैक्सिमम बेंडिंग मोमेंट. मैक्सिमम बेंडिंग मोमेंट. Which relation is correct for any design of beam? Okay, again I will explain. Moment of resistance means load carrying capacity. Load carrying capacity. Load carrying capacity. And bending moment means suppose बेंडिंग मोमेंट म्हणजे काय असणार आहे तर त्याच्यावर ऍक्ट मॅक्झिमम तेवढा लोड ऍक्ट करू शकतो. काय असली पाहिजे कंडिशन? डायरेक्ट सेकंड इयर स्टुडंट्स, ऑलरेडी यू हॅव स्टडीड this part in diploma, so I expect answer from your side. So maximum bending moment should be less than or equal to moment of resistance. That means जर तुमची लोड कॅरी करण्याची कॅपॅसिटी कमी आणि मी तुमच्यावर लोड जास्त अप्लाय करते, चालेल का? तुम्ही फेल होणार. तर तुमची लोड कॅरी करण्याची कॅपॅसिटी जास्त पाहिजे, मी जेवढा लोड ऍक्ट करते त्याच्यापेक्षा. तर आपल्याला डिझाईन साठी काय कंडिशन पाहिजे? मोमेंट ऑफ रेजिस्टन्स should be greater than or equal to maximum bending moment. Please remember this. Definitely one question is going to ask on this point. So moment of resistance should be greater than or equal to maximum bending moment. Okay. Then next. Now this is our example number 1. No, this is I think second example. Here example 1 is given. This is a steel wire of 20 mm diameter. Steel wire of 20 mm diameter is bent into a circular shape. Is bent into a circular shape of 10 meter radius. Of 10 meter radius. If E, the modulus of elasticity, is 2 into 10 raised to 5 Newton per meter mm square, then the maximum stress induced in the wire is. Then the maximum stress induced in the wire is. Now we will write which parameters are given. Okay, here